Okay, so for trapezoidal Riemann sums, you're doing the exact same thing as we did yesterday, only trapezoids. You're used to trapezoids looking like this. What we're going to do is have them look more as one of the sides being like straight, actually more so horizontal, and then these are going to be our bases. So when you put that on the graph, this is what your trapezoid's going to look like. So this one trapezoid, if you picture flipping it, this is your trapezoid you're working with. So when you set up all your trapezoids, you can pause the video. You're doing, 1/2, because that's the formula. The height is 1. So we're just talking about this. It's 1. And then your two bases are determined by your function. So 2 and 3. And then you keep going. And if you notice, if they're equal subdivisions, you can do some factoring. Take those out. And then you can notice there's a pattern with the bases. Because they're all next to each other, you can see that they double the ones on the inside. So that works for this rule specifically, but only if they're equal. So if we get into this one we're doing 4, so it looks like this is going to be 1, 2, 3, 4. So it looks like all my heights are 2s. Okay, so 2, and then here are my bases. So I've got one base and a second, so it's 1 plus 3, and then there's my trapezoid. Then I'm going to go on the next one, 2 again, base, or the two bases, are 3 and 4. Then, actually I'm going to cheat on this next one, because you see how it's just rectangle, right, because it's horizontal. So this I'm going to go 2 by 4. And then this last one, I get 1/2, 2, and then I get 4 and 2 for my trapezoid. And then if you add them all up, you get 25. Okay, so let's do more of a application question. So we're doing the outside temperature every hour, noon until midnight, according to the temperatures of the following table. What is their average temperature for the 12-hour period? Now, if you notice, these are all equally spaced. It's all 1. So all my heights are 1 for every single one. So I'm going to cheat a little. I'm going to do 12 trapezoids, and I'm going to factor out the half, factor out the 1, and what I'm going to have left with is all the bases that I'm going to cheat using that rule. So I know my first base is going to be 63, but then because these guys end up being next to each other, you're really doubling the 65, because you're going to have two bases, because you're going to have one trapezoid here and then one trapezoid right next to it. So you're counting that base twice. Then I'm going to go 2 times 66, 2 times 68, and then yada yada yada. 2 times 62, 2 times 58, and then my last base would be 55. Okay, so what I get then is 782. Now if you think about what that unit is, we're doing time times temperature. So if I'm doing time times temperature, it's kind of goofy because it's going to be like degrees Fahrenheit was the temperature, and then the time was like your height, which is hours, which is kind of a messed up unit. But what I'm doing is actually finding the average temperature. So to find the average temperature, I'm going to take my 782 goofball unit, Fahrenheit hours, and then divide by the total amount of hours, just like how you average like a test score. Say you average a test, you add 2 tests together, divide by 2 to find the average test score. Well, we're doing a 12-hour period, so I'm going to divide by 12, and it's hours, and you notice the units cancel. So we end up getting 65.17 degrees Fahrenheit. Okay, next one. All right, these ones have different subintervals, so you have to be careful. So your height's not the same, so I can't do that cheat thing. So if I'm going to estimate this, okay, I'm going to do 1/2. The height of the first one is 4, and then my 2 bases, 5 and 15. Then I'm going to keep going, plus 1/2. This one, the height is 1. And then my 2 bases. And then 1/2. Last one is 3. 17 plus 11. Okay, so if you add those all together, you get 98. Now, how do you know it's an over or under? Draw a huge graph, like doing increasing concave up, increasing concave down. Try to do every combination. Decreasing concave up, decreasing concave down. So increasing concave up, increasing concave down, decreasing concave up, decreasing concave down. And if you draw one giant trapezoid in here, you can see how that one is going to be an over. This one, if you draw a trapezoid, one giant trapezoid, this is going to be an under. This one, if you draw a giant trapezoid, that's going to be over. And last but not least, this is going to be an under. So, if you notice, the overestimates are all concave up. So, for trapezoid, it's all about concavity. Right, this is a little throwback. Change in population of the town over a 20-year period, where y is differentiable and increasing function. Table shows the population change in people per year, recorded selected times. Okay, so this is a little throwback. We're doing a right Riemann sum, 4 subintervals to approximate the area under the curve. So this one, remember, we're doing rectangles. So if I'm doing a right, my width is going to be, so if I'm going to integrate y of t dt from 0 to 20, this is approximately 4, and then because I'm doing a right Riemann sum, I'm going to be using this number. Then I keep going. My next one, between these two, my width is 6. And again, because I'm using a right Riemann sum, I'm going to be using the 3108 number. And then second one, 10 to 13 is 3. Using the right. And then the width for this one's 7. And again, using right. So 4283. So you can go ahead and calculate that. You can use your calculator. What does your answer in part A represent? Well, if you think about it, if we're looking at the units, right? We did people per year times the time. Years. Well, if you cross-reduce the unit, you're left with people. right? So the rate of change in the population over 20-year people. So after 20 years, the population went up by that many people. Okay. Assuming that y of t is a continuous increasing function, is your approximation part A greater or less than the true value? Well, continuous increasing, draw a picture. If the graph is increasing, either concave up or concave down, okay, if I did a rectangle with a right Riemann sum, I drew a giant rectangle on either of these, okay, that's going to be an overestimate. So my approximation is an overestimate because y of t is continuous and increasing.